Hello, this is Dr. Hisham Saeed. In this video, we'll learn about shear and moment diagrams using the method, the graphical method. But before we do that, let's review how we developed the shear and moment diagrams using the equations method. So we have here this beam, A, B, C. It's loaded in the middle, load P. So from symmetry, you can see that if we have two supports at A and C, there will be two equal reactions P over 2. And now we also learn now that P at point B is a discontinuity point, so I need to do two cuts to be able to draw the shear moment diagram for this beam. And if I do the first cut, for example, I'll find that the cut free body diagram will look like that. And when I do the sum of forces in Y and sum of moments, I end up with the first shear and moment equations. And we can see here that V1 is equal to P over 2, regardless of where exactly this cut between 0 and L over 2. And M1 will also be equal to, will be equal to Px over 2. So now it's dependent on where you make the cut. M will change linearly with the distance x. As another example, let's see this beam that's simply supported and loaded with a distributed load W. So from symmetry also, we can see that the two reactions will develop equal reactions WL over 2. Because if the length of the beam L and you have a distributed load W, so the resultant of that is WL, and from symmetry it's split between the two end supports. And we can see here that this W here is uniformly kind of the same over the length of the beam, so there is no discontinuity point in the middle. So I will need only one cut to develop equations for shear and moment. If I do the cut here at distance x, the free body diagram will look like that. And you can see that I have only M and V, one equation for M, one equation for V. So I'm not representing it by M1 and V1, it's just M equation and V equation, and we do the sum of forces and the sum of the moments, I end up with this shear and moment equation that can give you the shear and moment values for any distance x measured from the left of the beam. So when you just pause here and think about, look at the two examples that we have, and also if we try to find the relationship between the shear and moment equations that we have. So like V1 and M1 for the first beam and V and M equations for the second beam. So just pause a little and see if you can recognize any relationship between these two equations. All right, so after some pausing, you can see that the M equation is kind of an integration of the V equation. Or also the other way is that the V equation is the derivative of the M equation. So that's something we will we can see that using inductive reasoning, we can figure out, yes, it's actually V is the derivative of M and M is the integration of V. So that's inductive reasoning by seeing two examples here. But let's use deductive reasoning now and try to kind of come up with this graphical relationship or prove the graphical method that we will use, that amazing method that will save us a lot of time in drawing shear and moment, by using a deductive reasoning here. So what we'll do is the same that same beam with a distributed lobe will have a very slim segment of length dx. And we'll do kind of two cuts, have a little slim kind of section of the beam or segment of the beam. And I can see here if I do a cut at A, I will reveal here V and M internal forces, but at little distance dx, the internal forces in the other cut at the end of that segment at point B will be kind of M and V, but with little change, what we call here the dm, the change in moment, and dv, the change in the shear. So let's try to figure out what really happens over that little distance dx in terms of the change in the m and the change in the v. So if I do the sum of forces in y, and I can compare here the free body diagram to the sum of forces I have, I will end up with here negative wx is equal to dv. In other words, this means that negative w is equal to dv over dx. That rate of change dv over dx is equal to the value of the distributed load, but now negative that value. So once you see negative, then let's hold our horses here a little and agree on what's the sign of w. What would be a positive w or negative w? So a positive w is any load that pushes the beam down. That's actually a positive definition of a positive load. Loads are generally going with the gravity. And then a negative w is a load that pushes the beam up. So this means that if typically if a load is pushing down, so this means that it's a positive load, so that means that it's a negative slope. So here the slope of the shear diagram, slope of V diagram, is equal to negative the value of the load I have. So if this W is constant, meaning that this distributed load is uniformly distributed, it's just the same value over every unit length, this means that the slope of the shear diagram is constant. What is a figure or a curve that have a constant slope over any point of the figure or the graph? It's a line graph, right? So a line graph with a fixed slope. But if the magnitude of W is increasing, meaning that the W here is not uniformly distributed, it's maybe a triangular distributed load. So this means that the slope of the shear increases, which means that this is actually the shear diagram is a parabolic curve or a parabolic shape here. So that's kind of an interesting observation, that the value of the distributed load at any point of the beam is the slope of the shear diagram on that point. And let's do the sum of the moment of that free body diagram of this segment of the beam. And if I do the sum of the moments at point B, so I have here the moment on the left face of the segment, M, and also the moment on the right face of the segment, M plus dm, and I have the negative V dx, that's the negative moment from the shear on the left face of the segment, and then I have W dx times dx over 2, kind of the resultant of the W over that little distance dx times half of dx as the moment arm. So kind of rearranging the equation, that will give me that dm is equal to V dx minus W dx to the power 2 over 2. Now let's remember that dx is already a very small distance. Now dx to the power 2 will be really very small, almost close to 0. So I can cancel that term here, and we'll end up with that V is equal to dm over dx, or in other words, the slope of the value of the shear at any point is equal to the slope of the moment diagram at this point. Kind of similar to the relationship between W and V, I'm driving now a similar derivative relationship between V and M. So if the value of M as a magnitude is constant, this means that the slope of the moment diagram is also constant over the length of the beam, which means that M diagram here is a line. But if the value of the shear is increasing, then this means that the slope of the moment curve or diagram is increasing, which indicates that the moment diagram is a parabolic shape. So let's summarize here. So the load and shear and moment derivative relationship. So if I have this beam here with that kind of already kind of of course this is not a uniformly distributed load, it's kind of a parabolic distributed load as a function of x. So the value of the load is the slope of the shear diagram. You can see here at point A, the value of the load here is 0, so that means that's a 0 slope for the shear. So that's a value here, the slope here is horizontal. And then the maximum load value is WB, which kind of, you can see it here, that's a big slope of the shear at point B. All the slopes here between A and B, except for at point B, A exactly, or the slope here is negative because W is positive. And remember that negative that shows here between the W and dV over dx, that relationship. On the other hand, the value of the shear at the point is the slope of the moment curve or diagram at this point. So if I have VA, which is the shear at A, which we'll learn how to get it, but VA here is the value of the shear at A, so it's a big value here, positive, so that's a positive slope for the moment at A. Go all the way, that value of VA decreases all the way until it ends up with zero value at somewhere along the beam length. So this means that my positive slope of the moment decreases until it reaches a negative slope, or the point of maximum moment. And then you can see here the shear value flips from positive to negative. So this makes the slope of the moment flips from a positive slope to a negative slope, meaning that from increasing in the value into decreasing now until it reaches the maximum negative slope at B, which then brings the moment curve into a 0 point at point B. So that's the derivative relationships between the load, the shear, and the moment. These are more examples here, so just to confirm that derivative relationship. So if we see here that this distributed load here, WO, is uniformly distributed between these 2 points, the left and right of this beam. So it's the same value of W, so it's the same slope of the shear. So it's a linear relationship for the shear curve. If we look at the second beam, it's a different story. You start with a small value of load, and it's a distributed load that increases now from W1 to W2. W1 is a small value, so this means that it's a small slope value. Remember, W is positive, so it's a small negative slope for the shear. And then this negative value of the slope increases more. So it becomes more and more negative slope. So this makes it parabolic, and the shear curve here goes down. And it's the opposite for the third beam. Still, the beam here, the shear goes down, but the rate of decreasing is larger at the point of W1, because W1 is larger than W2. But generally here, your shear decreases from the left to the right, because you have a distributed load that pushes down. So that's a negative slope in both cases, but just the change here is different. Now, if you look at the relationship between M and V, V1 here and V2, so V1 is a large positive value, so that's a large positive slope, and then, which decreases to V2, which is a smaller value positive, so it ends up with a small slope value at the M2 here. And then we can kind of see similar observations for the other two beams. So now let's go back to the same beam. Kind of remember the derivative relationships we kind of figured out using that deductive approach. We proved it by that segment dx of the beam. Now if I look at these relationships, and for the first one, what about if I integrate that relationship relative to dx, I integrate dv. So that means that I'm now getting a value of v, and if I'm thinking about I'm integrating over a distance between points A and B, so that brings me the difference of shear between points A and B, which would equal to the integration of negative Wx. What does this mean? That integration, it's the area under the load diagram between these 2 points. So now I can, with the derivative and the slope information, I can also draw the diagrams by calculating the difference in the shear value between 2 points by looking at the area under the load diagram or shape that I have. And also we have to remember that downward load decreases V and upward load increases V. That negative in the formula here, that negative sign in the formula kind of flips if you have the load is when the load is positive, which means it's going down, that decreases the load. So kind of we follow the same direction of W to figure out how V is going. Is it decreasing or increasing? So W goes down, V goes down. If W goes up, then V goes up. Or so that's kind of how I can figure out if my V increases or decreases. And then also remember, we'll have here some exception that point loads causes sudden changes in the V, so jumps or drops in V, like we'll see in examples later. Now if I look at the second relationship and I do a similar integration here to figure out now the difference in the moment between 2 points, which will be equal to the integration of the shear diagram curve between these 2 points. Integration means the area under the shear diagram curve between the points A and B. And positive, when I calculate this area, it can be positive or negative. So positive V area between 2 points means that the moment increases between these 2 points. And the negative means negative value for the shear area means moment decreases. And point moments, which can happen, point load moments or point reaction moments, can cause drops or jumps in the moment diagram. And it depends on the direction of M, that load or point moment. So let's see an example here. If I have a simply supported beam with a moment point load in the middle, ML, so I will have reactions develop AY and BY in this way to resist that counter clockwise moment, and that counterclockwise moment will be resisted by a clockwise couple of moment from these two reactions AY and BY. And if you can see here, of course, that's a discontinuity point in the middle, so I have to do 2 cuts. And if I do the free body diagram of the 2 cuts here, you can see the second cut I have ML showing up as a counterclockwise moment. And if I do the equilibrium of the internal forces here, I'll find that M1 in the first cut is in equilibrium with AW and the moment and the length X here of the cut, but now the difference between M1 and M2 is basically ML. And ML is going counterclockwise, so there should be internally a clockwise moment resisting it. A clockwise moment is opposite to M1 in the first cut, so this means that the moment in the second cut drops suddenly, because in internal forces we know that a counterclockwise moment is positive. So if you, to counter ML, you're adding a clockwise to the moment internal force value of the moment, internal moment value here. So it will end up with M1 negative ML. So that's a drop. You're dropping from M1 to M1 minus ML. So this is how we draw the curve here. If you go increase here until M1, just before the application of ML, and then once you add ML, you will drop your moment diagram value from M1 to M2. And the difference here is basically ML. So let's build on that and kind of maybe summarize the relationship between W, V, and M from integration perspective. So these are the two relationships. And if I'm talking here about focusing on point A and B along the length of the beam, so the delta Vm, or the difference between the shear between points A and B, will be basically equal to that hatched area and the load. So kind of need to go back here. That's too much than I should show. So the area, the difference in the shear between A and B would be equal to that hatched area in under the load curve. And then if I consider the area under the shear curve between these 2 points, that will result in delta M AB, the difference in the moment between these 2 points A and B. And remember that because the area here is under the curve of V, and the curve here has positive values, so this area is positive, so this means that the moment increases from A to B. You're adding a positive value to the moment at A, so you're increasing to a higher value at B. And kind of if I can do the same with if I pick any other 2 points. In this case here, I'm picking after the shear becomes negative. So now the area is negative under the shear curve between these 2 points, which means that the moment is dropping. You're adding a negative value of the area shear here. So your moment between these 2 points is dropping. And this is an example to show here what's the impact of point loads, point forces, and point moments. So I start here with a force going up, V1, or shear going up, V1. So this means that's I'm going up here a positive value V1. I don't have distributed load, so W here is equal to 0. So the slope of the shear diagram is 0. So you just basically go flat, horizontal, until you hit P. And once you hit P, you drop with it a P value, with a P drop value in the shear diagram. And then there is no distributed load, so you go horizontal, W is equal to 0, horizontal slope, until you hit V2, which brings you down to 0. If you relate this to the moment, so the V1 here, the positive value V1, is a big slope at the moment. And you can see here, V1 is just a constant value until the mid of the beam, and it's constant, the same value, so it's a constant slope for the moment until it hits the load, which changes the shear value V to V2, which is a smaller value, so your slope goes high until the middle of the beam and then changes to a lower value, the slope, a lower value, so that gives us that shape of the moment. For a point moment, you don't have any impact on the shear diagram, but you can see here that if this moment here is a counterclockwise moment, so I see here that I'm dropping the moment value by this point moment value, MO. And you can see the slope of the moment diagram in the second case here is the same. It's just the same slope of V, because the shear value along this segment of the beam is the same, is equal to V. So it's the same slope, but once I hit the moment, I drop, and then I continue with the same slope, increasing here slope, or positive slope, for the rest of the beam. So that's it. This video here is introducing the basics of the graphical method to draw shear and moment diagrams. We will see in other videos how to apply that in examples. So the examples will clarify a lot how we actually apply the graphical method. But we know now that there are two relationships that relate the shear and moment diagram. There is the derivative relationship that gives us an idea how the slope of the shear and moment will look like. And then there is the integration relation, which will help us to calculate the difference in shear and moment between different points in the beam. So thanks for watching, and I'll see you in other videos to see more examples of the graphical method to draw shear and moment diagrams. Take care.